Okay, good morning, everyone. Let's get started. We are approaching the end, at least, of the assignment streams. So for the undergrads, next Monday, you will be submitting your results for the 10th and final assignment. You're almost at the end. Good news, bad news. It's not the end, it's the end of the beginning. When you finish assignment 10, you will have an experimental platform that you can complexify in pretty much any way you want within reason, and to elaborate that into your final project. And we will talk about, next Tuesday, we will talk about what that final project should look like, what the expectations are for you as you're working on your final project between next Tuesday and the end of the semester. For those taking the course for graduate credit, as I mentioned, I was running a few days ahead of you, creating the differentiable assignments for you to do. I fell a little bit behind. I didn't finish making the differentiable assignment until Tuesday, so I pushed back the submission deadline for those taking it for graduate credit. So you all can submit D5 by 11:59 p.m. next Tuesday rather than next Monday. And then grads, you're also tackling the final project, and we'll talk about expectations for the grad students as it relates to the final project next Tuesday. So we're almost there. We'll pivot next week. All good? Any questions about this final mile in terms of assignments? Question?
For the undergrad assignment 10, is that like, is that like a pretty big assignment, like time-wise?
Yes, it is a pretty big assignment time-wise. It's not the most intellectually challenging of all the assignments. It's basically ripping out this minimal robot, nine links, 8 joints, relative absolute coordinates, joint normals. There's a lot of finicky pieces, so leave yourself time to work on assignment 10. And as I mentioned last time, don't race. Do everything in baby steps. Add one link, one joint at a time. Debug everything. Make sure everything is literally in the right place and moving in the right way before you add the next piece to the quadruped. Okay, any other questions? Okay, so back to our lecture material. We are in this module on looking at open challenges in the field. These are major challenges that are keeping evolutionary robotics from designing a dishwasher cleaning up robots and snow blowing robots for us and all the rest. Where are all the robots? They're not here, at least in terms of evolutionary robotics, because there's a number of problems we got to solve first. Most of these problems are known. There are partial solutions that have been formulated in the literature, and we've started to look at some of these. And we started in last time on looking at some of the potential solutions to the most challenging problem, not just in evolutionary robotics, but robotics in general, crossing the reality gap. There are many attempts to cross the reality gap in the literature. I picked 4 representative examples. We looked at the first one last time. It's got a fancy name, but a relatively simple idea. Sprinkle noise into the simulator so that when the evolutionary algorithm simulates robots over and over again, the evolutionary algorithm never steps into the same river twice, which Heraclitus said 2,000 years ago, right? Everything is always kind of changing, so the evolutionary process can't exploit artifacts in the simulation that are not real in reality. Works okay, but that solution in turn has some problems or some open challenges, which is where do you put noise, how much noise do you put, and so on. So a solution, but a partial solution. Last time we started to look at the GOLEM project, which is a completely different way to attack the reality gap problem. What's the overall intuition behind the GOLEM project that we introduced last time?
Did we look at it last time?
I mentioned it last time.
Is it like diversity? It's like having many examples of variation.
Absolutely. You shoot an arrow at the target and you miss the bullseye, shoot another arrow, and another, and another, and another, until you eventually get lucky. Okay, so that's the idea behind the GOLEM project, which was reported in the literature in 2000 and ended up on the New York Times the next day. Basic idea is we're going to use this brand new technology at the time, which was a 3D printer, to evolve robots as we've seen many times in this course now, and then hook up the simulator to a 3D printer and basically reduce the time and effort it takes us to actually manufacture one of our simulated robots. And if we do enough automated design by evolution and automated manufacture by 3D printers, we can design, manufacture, and if a lot of those robots don't cross the gap, who cares? We keep going until we get one that does. That's the intuition underneath the GOLEM project. Yeah? Okay, we ended last time by starting to walk through exactly how the GOLEM project works. This experiment is broken up into 3 phases. First phase is going to look very familiar to us. We're going to evolve a robot to locomote in simulation. And then step 2, we're going to manufacture the robot with a 3D printer. Step 3, at that time we couldn't print all the parts of a robot, so there's still a manual part to the manufacturing process. Okay, something that was kind of new that we saw last time is that when the GOLEM researchers evolved their robots in simulation, they were not just evolving sets of synaptic weights for a manually designed robot with a manually designed cognitive architecture inside. They're broadening the evolutionary algorithm, and they do that by modifying the data structure that encodes the genotype. They've got a more complicated data structure here, where this data structure is now a blueprint dictating how to build the brain and the body of the robot. Yeah, and we were walking through this data structure last time. So top level, a genotype is made up of 4 variable length lists. In your case, you have one single vector, which is the set of all synaptic weights. Here we've got 4 variable length lists. As the names imply, the first list encodes a set of vertices, which become the points that you see in the robot here. The next list is a whole bunch of bars that connect pairs of points together. The third list is a whole bunch of neurons. In this cartoon example here, this particular genotype is specifying this phenotype down here. Phenotype is now not just the brain of the robot, but the body as well. The phenotype in this cartoon example has 5 neurons inside, and you can see that each of the 5 neurons has a synapse connecting it to every other neuron. And you can see that in the description of a single neuron down here, one element in the neurons list, we have a threshold for the activation function of that neuron. And then inside this list is another list, which is the synapse coefficients or the synaptic weights. So this genotype is a little confusing. It's a whole bunch of lists embedded in lists embedded in lists. Hopefully you get the idea. Yeah? Okay. The last piece that we ended with last time, the 4th and final list, is a list that specifies all the actuators that make up the robot. These are slightly different actuators from what you've seen before. A description of an individual actuator, that description specifies some bar inside the body of the robot. So we pick a bar. It also specifies a neuron. So we're holding on to a bar. We find the neuron that's being specified. Let's imagine it's this neuron here. The actuator takes the value arriving at this neuron and sends it to the actuator that's going to be embedded in this bar. So the minute an actuator points to a neuron, that neuron becomes a motor neuron. Okay, question?
So how do the actuators move?
How do the actuators move? Exactly. Okay, there's a hint here, which is the 3rd and final number that describes an actuator is the bar range. Again, it's kind of cryptic, but it might give you a hint. So what do you think is going on here in terms of the actuator? We're embedding an actuator in a bar, not maybe where you might expect, which is up here. We're not dealing with rotational motorized joints, which you've been dealing with in all the assignments, something different.
Like a piston shape to it? That's just the length of the piston?
the length of the piston. What is the maximum and minimum length of the bar that can be achieved by a piston that's going to sit inside the bar? So you can imagine that as you walk along the actuators list, that actuators list is going to contain a bunch of these things. Each one points to a particular bar, and every time an actuator points to a bar, imagine we cut that bar in half, pull it apart a little bit, stick a piston into it, and then connect a neuron to the piston. Imagine that neuron at a given point in time is containing a positive floating point value. What do you think that motor neuron is telling the piston to do? Expand. If that motor neuron is encoding a negative floating point number at a given point in time, it's telling the piston to pull. Got it? Okay, so that's it. We've got a genotype which tells us how to construct the body and brain of a robot. We've got our phenotype here. We do what we normally do, drop it into a physics engine, which was brand new back in 2000, and assign a fitness value to how well that robot moves from left to right along the virtual floor in the physics engine. Exactly like we've seen before. Okay. So let's talk a little bit about the evolutionary algorithm. They start with an initial population, not of random genotypes. You could imagine just creating a whole bunch of random lists with random floating point values in it, and that would construct some random morphology and some random neural network. They didn't do that. In this experiment, they created a population of 200 genotypes, and each genotype is null. Null meaning it's an empty list of empty lists of empty lists. There's nothing in the genotype. Kind of an odd choice. So we know by definition that each of the 200 phenotypes of those robots are null phenotypes. They're all going to get a fitness of 0. They don't even create a robot that moves at all. Kind of a strange choice. We'll come back to that in a moment. Fitness, this is very familiar. Displacement of the center of mass. How many time steps do they evaluate the simulation for? If you go and read the paper, it doesn't give you number of time steps. It says fixed number, and that fixed number was 12, of cycles of the neural control. This sounds kind of cryptic again, but we've seen, so it should give you a hint about what the neural control is doing. What does 12 cycles mean, or what could it mean?
It's kind of like attempting 12 steps, like if locomotion is a cycle.
Okay, if locomotion is a cycle, this thing is going to breathe 12 times. The motors are going to increase, or the pistons are going to increase and decrease. But those cycles are being dictated by the brain, by the neural network. And they said cycles not of locomotion, but of the neural controller itself.
Is it sense, think, act cycles?
That's a good guess. In your assignments, it is, right? During each time step, if you have 100 time steps in your simulation or 1,000 time steps in your simulation, you're doing 100 or 1,000 sense, think, act cycles. It's a good guess. That's not what they mean.
Parameter updates,
Parameter updates? Parameters of what?
weights of the neural
It could be, but remember the weights are ultimately going to be updated by the genotype. So we're just talking about evaluating a single robot in a simulation. During the simulation, during your simulations, the parameters of the neural network, the synaptic weights, do not change. So another good guess. This is just evidence that they should have worded this more carefully.
Do you mean like 12 evolution cycles?
Not quite. No, we're inside the evolutionary algorithm. We're evaluating one robot in the physics engine.
Does the neural network have one of those like pulse neurons in it?
It has a pulse neuron inside, which they don't mention explicitly. I know the authors very well. Shame on them. There's a CPG sitting somewhere in here. It's a CPG neuron that is emitting a sinusoidal pattern. And they wait for that sinusoidal, as they're running the physics engine and the time steps are elapsing in the physics engine, they let that CPG emit 12 cycles. And when it's done, that sinusoidal pattern is done repeating 12 times, They end the simulation, they measure how far the robot has traveled in the simulator, and assign that single distance, that single floating point value to that robot and its genotype.
Can that like pulse evolve over time, or is that like constant in every step?
It sounds like it's a good question. Again, they didn't specify, but I would infer from this that it's fixed, that all the sinusoidal patterns in every robot, no matter what its body or brain looks like, has more or less the same frequency, I think. So far, so good? Okay. So some familiar concepts, some new concepts here. Why did they start with a null robot? Let's draw the null robot right down here. I've drawn nothing. There's no phenotype. So the first generation of this evolutionary algorithm is kind of odd. They're stepping through each of these 200 genotypes. There's nothing there, so there's no robot to create. Don't even need to bother running a simulation. You assign a fitness of 0 to all of these 200 genotypes. How do you delete the ones that have lower fitness? You can't, because everybody has exactly the same fitness. 0, flip a coin, delete half of them survive, and now we start to make randomly modified copies of the survivors. So far, so good? Okay. So randomly modified copies, they're going to take these null genotypes that have survived, and they're going to start to randomly modify them. They're going to apply mutations. Remember that in your underlying code base at the moment, you have a fixed vector of floating point numbers, which specify the synaptic weights for the neural controller for your robot. You have one and only one mutation operator. Whenever that mutation operator is called, it picks some number, it picks some index in your vector, and then generates a random number and sticks it into that element, right? One and only one mutation operator. In the GOLEM project, there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 different mutation operators. 10 different ways that the evolutionary algorithm can take the genotype, this thing, and make a random change to it. Question?
If the changes are random, why wouldn't they just populate it with random numbers?
I don't know. I don't see why they couldn't have done that. Probably an arbitrary choice.
I think in the original NEAT paper, they were arguing that you start with the simplest thing and then you add complexity only as it is justified. It seems like similar to what they're trying to do.
Good point. Actually, that's a good point. Maybe they wanted to make sure that they were starting with sort of the simplest robot you could imagine, and then let evolution gradually complexify things if it's needed. And what's the simplest possible robot you can imagine? The null robot, just nothing. Okay, so we have these 100 surviving null genotypes. We're picking one at random, and that becomes the parent, and we're allowing it to create a child. We're going to copy that null genotype, but when we do, we're going to roll a 10-sided dice. We're going to pick one of these 10 mutation operators at random, and whichever one we pick, we're going to let that mutation operator mutate that null genotype. So far, so good? Okay, so here's a cartoon showing a possible way this might happen. And all we're seeing here are the phenotypes, the bodies and brains of this lineage of robots. We're starting with the first ancestor, which is a null phenotype. We roll a 10-sided die. Whatever that die is, we apply that mutation operator. Which one turned this null phenotype into a single bar with a short length? Out of these 10, which is the one that was chosen? Which one turned this null phenotype into this non-null phenotype?
3. Add a dangling bar.
Number 3, add a dangling bar. Absolutely. So we've got a little bar here. So this is the child. You take this little bar and you drop it into the physics engine, and that little bar travels forward by 0.01 millimeters in the simulator. It's got a higher fitness than its parent, kills off its parent, and now it enjoys the privilege of being able to produce an offspring of its own, which it does. Whatever the genotype is for this phenotype is copied. And when we're copying that genotype, the evolutionary algorithm again rolls a 10-sided die. And that mutation causes the child to look like this. Which mutation operator was applied to the grandchild? Number 1, change the length of the bar. Everybody get it? Okay, question.
What are the percentages account for? Like that doesn't add up to 100%.
20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. You're right. Good question. I'm imagining that's a typo. It should add up to 100%. Okay. Next one. What turned this into this? 1. So we lengthened the bar. Now there's a red circle. What's the red circle?
Is that a neuron?
It's a neuron. Yep.
So it's 5.
Number 5. Number 5, add unconnected neuron. So now this robot has a brain, but the brain is not innervating the body. Whatever the value is in this neuron, which is probably the CPG value, it's not affecting the behavior of the robot.
Are the percentages representing the percentage of times that those options were selected, or is it something about the impact of them on evolution?
More the former. So I mentioned a 10-sided die, which assumes that it's a uniform probability of picking these 10 mutation operators. It's not. Imagine it's a weighted die. These percentages should add up to 100%. And the investigators had some intuition that some of these mutation operators should be applied on average more often than not. Why? Why not just leave everything as a uniform probability distribution? Any of these 10 could happen with equal probability.
Not everything should have the same impact on the behavior of the robot at the end.
Some of these mutation operators, you can probably guess, have a bigger or smaller impact on the brain and body of the robot, and thus on how it behaves in the simulator.
But if you do that for the mutations, why you start from a null robot? You should make a guess that that's probably gonna take you extra computation to get to some point.
Probably yes. I don't know. It's also balanced against them trying to start with something simple because, again, computation is expensive, so they want to start with a very small robot, a very simple robot. A lot of arbitrary choices here, I think, in this experiment. Okay, how about this one to this one? What mutation operator or operators hit this genotype as it was being copied?
That's lengthen a bar.
Lengthen the bar, number 1, yep.
Add a neuron and also add a connection.
Add a neuron, and although it doesn't say here, every time we add a neuron, all of the other neurons that exist in the brain connect to it. Yeah, so it's always a fully connected network. Every time we add an unconnected neuron, it doesn't stay unconnected for long. Everything else attaches to it. Which means we need new numbers in the genotype. We need to specify the weights. We need to specify the weights of those connections that are arriving at that neuron, so they've got to generate more random numbers. So some of the ways in which these mutation operators are being carried out is sort of implied, but hopefully you get the idea. Let's jump ahead to this one, to this one. You'll notice something special has happened here. What's happened?
The brain is connected to the body.
Okay, how so? What mutation operator caused that to happen? Number 9, attach neuron to bar. Yeah? So we're going to attach this neuron to this bar. You'll notice this bar is now cut in half, which is a visualization of the fact that this piston has been placed in the midpoint of this bar. So we're adding an actuator and innervating it with a synapse although the name of the mutation operator kind of implies that. It doesn't say it explicitly. So far, so good? Okay, so you could imagine somewhere else in this initial population of null phenotypes and genotypes, another set of random choices of mutation operators will create robots with different bodies and different brains. Questions? Okay. Okay, I think we worked our way through this. Okay. Again, I apologize for the image quality here. Hopefully you can see. Here are a whole bunch of samples of the kinds of robot bodies that existed partway through evolution. And we're looking at not all 200 robots, but just a sampling of them. They're partially evolved, so they move to the right a little bit at this point in evolution. What observations can you draw from what's going on in this particular evolutionary run?
Pyramids are cool.
Pyramids are cool. Why are pyramids cool? They are cool. There's a reason why. They're stable. Yeah.
I'm guessing there doesn't need to be a lot of coordination to get it to move in a direction. Like two things can expand and it'll push it, whereas like a worm would be harder to do.
Absolutely, right? Mother Nature is wonderful, but she's also lazy. She's a satisficer. We asked her to design something that moves from left to right using this kind of encoding of genotypes and phenotypes. Turns out that pyramids are cool. They're a relatively easy way to do things.
I was gonna ask, does the sort of set of mutations that you had on the previous slide, that makes it pretty difficult to evolve a big brain, right?
I don't know. Does this particular choice of how to encode the robots bias the evolutionary algorithm to small brains, small bodies, big bodies? Remember our discussion about HyperNeat last week? HyperNeat was designed several years after this experiment to try and solve this problem. We actually want to control where we focus evolution's attention. We want to focus evolution to search the space of all symmetric, repeatable types of patterns. No matter what genotype and phenotype encoding we pick, whether we know it or not, we're biasing evolution to search more intensely in certain parts of the space of all possible robots than others. Maybe we're biasing evolution towards pyramids. Maybe that's the reason why we get pyramids in this experiment. Not necessarily that they're useful, but that's where it tends to focus its time. Are we focusing evolutionary search on the subset of robots that have small brains or big brains? Maybe yes, maybe no.
One thing that comes to mind is why attaching or detaching the neurons to the bars is one choice of the mutations, and it should not be just as soon as a neuron is added, you connect it to the robot.
Okay.
You will have like some robots that are not connected to neurons, then how are they moving?
Okay, right. So we could decide, we could make a change to the way we map genotypes onto phenotype, that every time we create a neuron, it's a motor neuron and it's got to attach to some part of the body. That's also a choice. How is that going to bias evolutionary search? What kinds of robots is the evolutionary algorithm going to generate more often than not if we're using that kind of mutation operator?
Is it going to create robots that are like, they don't have like a very developed like brain before like they begin making impacts on the robot itself?
That is true. Now, whether that's a good thing or a bad thing, who knows? But that's right. As mutations start to elaborate the cognitive architecture, the number of neurons and connectivity in the brain of the robot, every one of those neurons is going to connect to some actuator in the robot's body, which is going to mean that all of the bars are actuated, or most of them are going to be actuated, which may or may not be a good thing, right? It's hard to say. We could try it. We could alter the mutation operators, run evolution again. We're going to get robots that have more active components inside their body. And maybe the evolutionary algorithm can evolve synaptic weights to coordinate that motion. Or maybe that's too much too soon. It's not the evolutionary algorithm is not able to. You could make an argument either way. So this is part of the reason why a lot of these choices tend to be arbitrary. It's hard to know in advance whether what you're putting into your genotype and phenotype is going to make things easier on the evolutionary algorithm or harder on the evolutionary algorithm.
It seems like the goal of this is to evolve a body that doesn't really require much coordination to move.
I don't know whether they planned that in advance, but that was a result of this experiment. That you do, as you'll see, and I'll play some videos for you in a moment, you don't need much. These robots don't need much to get going, to start moving. Okay. One of the things you can take away from here is, again, there are some common themes. You tend to see a lot of pyramids, but also a fair bit of diversity. The bodies look kind of different. We haven't converged on one and only one body plan. You can infer from this that if the bodies look diverse, the brains are also probably diverse as well. There are probably different brains in these robots with more or less neurons, so different cognitive architectures, different synaptic weights in them. That's usually a good thing. This is a horizontal cut through an evolving population. So evolution is running. At some point, they paused evolution and looked at all the bodies and brains at that point in evolutionary time. Sorry, that's a vertical cut. Here's a horizontal or longitudinal cut through the same evolutionary run. It may be hard to see in the back here, but this robot has a number 4, so they're assigning a global counter. They're just keeping count of all the robots. Here's robot number 4. Here's robot number 60, number 82, 117, down to 198. So here's a fossil. This is from early in the evolutionary record, and here's an existing organism. This is something that exists towards the end of the evolutionary trial. Again, it may be hard to see. There's some fitness values assigned to all of these, F equals. A lot of these F equals are 0, so these are not necessarily good robots. F equals 0 means the robot doesn't move at all. Some of them have a non-zero value associated with them. Some are moving, some are not. They're just trying to take slices through this evolving population to kind of see what things look like. Okay. Here was an attempt to try and do this, not in an anecdotal way by just looking at screenshots, but to do this in a quantitative manner. If you've ever taken a biology class, you've probably seen a picture that looks like this before. These are phylogenetic trees. We've got usually a root up here somewhere. This is a common ancestor. In this example here, this particular robot existed in the population for many, many, many generations without producing any offspring, so it actually survived somehow. At this point in evolutionary time, it produced 1, 2, 3 offspring, and those offspring in turn started to produce a lot of offspring, and so on. There's many, many different ways to draw a phylogenetic tree. The choice that the investigators made here is to draw evolutionary time on the vertical axis. So here's the first generation, and here's the last generation down here. Usually we've been drawing evolutionary time on the horizontal axis, where time unfolds as we move to the right. Kind of an arbitrary choice. The horizontal axis represents ancestral proximity. What do you think they mean by that?
Like, if you have like the phenotype vectors, it's like probably like the distance between the two. I'm sure there's a way to calculate just like how close they are.
There is a way to calculate how close they are. It's not based on the phenotype, strictly speaking. You could take the phenotype and measure the similarity of phenotype. The more similar they are, the closer they are horizontally. The more different their phenotypes, the further away they are horizontally. You could absolutely draw a phylogenetic tree like that. It's not quite what they did.
Is it like the performance?
It's not performance. Good point. Actually, nothing here has to do with fitness. Fitness is not visualized at all here. Ancestral proximity.
Is it based on like number of steps of evolution since they were the same?
Since they were the same. So brothers and sisters, most of the time in this picture, should be drawn close to one another horizontally. First cousins a little bit further apart horizontally, second cousins, and so on. It's not quite true. It's a little more complicated than that, because you can see there's one parent up here and 3 siblings down here. These 3 siblings should be drawn right next to one another horizontally. There's some other things going on in the way they drew this, but generally speaking, the idea is to get a family tree. You have the ancestor at the top, and then you have more and more children if that particular lineage or that family is successful and is producing highly fit children and grandchildren and great-grandchildren. You see a lot of these trees tapering off as branches of this tree die out. So let's just take this little tree down here. Here was sort of a cluster of the family, a branch of the family that for whatever reason got some fitness, but not as much fitness as this branch of the family. And this branch of the family eventually outcompeted this branch of the family. That's why it's drawn in this way, to help you see those kinds of evolutionary dynamics going on. Okay, so let's have a look at, and last thing I forgot to mention is links themselves connect parents to children. Okay, first thing to notice, in this particular evolutionary run, they got divergence. So they had way up here at the top, one ancestor. This was probably the first non-null phenotype, the first thing that actually moved in the simulator. It produced 1, 2, 3 children way up here at the top, and all 3 of those children were successful. They started to produce their own branches, and by the time we get down here to the end, we have familial diversity, meaning we've got some brothers and sisters, we've got some first and second cousins, we've got second, third cousins, 4th, 5th, 6th, 7th, 17th, 18th, 22nd cousins. We've got a diversity of individuals that have to go further or shorter back in time to find a common ancestor. That's good news, right? That generally suggests you've got a lot of diversity in the population. 17th cousins that have to go back 17 generations to find a common ancestor, they have probably diverged quite a bit in terms of the makeup of their bodies and brains. So we've got a lot of phenotypic divergence, which isn't being plotted directly. We're inferring it from the fact that we have a lot of familial divergence or variance. Question?
Would convergence indicate that you have a more successful robot per se?
Convergence could mean that, and that happens in nature as well. You have individuals that have a common ancestor way, way, way back in evolutionary time, but evolutionary pressure is tending to push everyone in the population towards one and only one solution, because there's one and only one way to do things. That's actually also possible. Maybe all of these things down here seem diverse, but if we actually looked at them, they're all pyramids. You'll have to trust me that that's not the case in these experiments.
Is that like everything is evolving to become a crab?
Everything is evolving to become a crab, right? What is it? I forget what the term is. Carcinogenic, thank you. I can never say that term. Exactly, right. Turns out, funnily enough, there tends to be certain ways to be in this world, or at least on this planet, that are better than others. And the winner at the moment seems to be crabs. Not us, crabs. Okay, good point. Thank you. Okay, they reran the evolutionary tape. They started evolution all over again with a set of 200 null genotypes, and ran evolution forward again. But now these null genotypes were being hit with different mutation operators and different sequences of mutations that led at the evolutionary scale to very different dynamics. Here we get convergence, as was mentioned in the back there. We've got a whole bunch of individuals down here. We've got 200 individuals down here, which all have a relatively recent common ancestor. It's in here somewhere. Everybody see that? These 200 robots probably all look very similarly, if not identically, and probably all move similarly, if not identically. Over here, we get the emergence of species. We had two individuals way back early in evolutionary history that were both successful and spawned massive families so big that maybe we want to refer to these as species. This is a little bit tongue-in-cheek. These aren't exactly species. Why not?
They all share a common ancestor.
Not quite. If they were species in the strict sense of the word, what would they be able to do or not able to do?
They would not be able to like sexually reproduce.
They cannot sexually reproduce. There is a sexual recombination operator in here, but in the interest of time, we're not going to talk about it. These species can sexually reproduce. Whether that produces viable offspring, I have no idea. They just wanted to show that even in this evolving population, you can get, in some cases, just by chance, you can get distinct subgroupings of robots. Over here, we have all except one individual, this individual, in the population that are all similar. These are all dinosaurs. They're all doing fantastically well for a very long period of time. And then this one individual here that had pretty good fitness good enough to compete among all of these, but unlucky in the sense that it never produced any offspring. Until, at this point, just by chance, it happened to produce 3 offspring that very quickly started to exhibit faster motion than the dinosaurs over here, and the mammals over here quickly started to proliferate and drove this subpopulation of robots to extinction. So even a relatively simple evolutionary algorithm, you can start to get rich evolutionary dynamics. Your evolutionary algorithm is probably too simple to see any of that. But again, I wanted to spend a minute on all this. Might be an interesting idea for a final project. Can you complexify your evolutionary algorithm so that you start to see ecological or evolutionary dynamics like speciation, extinction events, and so on? If you're interested in that, come and see me in office hours and we can talk about it. Okay, crabs. Right? Crabs are a good way to do things. Pyramids are another good way to do things. Here's a few examples of what they got from 2 different evolutionary runs. In one, they got robots that looked like this. And you should already start to see now at this point why pyramids are good. Why are pyramids good? Good in the sense that it doesn't take evolution much to cobble together something that actually moves in a forward direction.
Does it consistently make it so that the force that's being applied is only being applied in one direction?
Exactly, right? If you push directly against the floor with a normal force, you don't go anywhere. But if you have a body and a brain that allows you to continuously push against the ground at an oblique angle, and you always push with that oblique angle, you're going to consistently keep moving in a given direction for a while, right? A simple hack that evolution tends to find in this space.
So in these top ones, is there only one motor that's being used?
Is there only one motor? I think there's 2. It's a little difficult to see. There's one here, and I think there's another one in here somewhere. One or two. It probably doesn't need the second one. One is probably sufficient. Okay, carcinogation, whatever it's called, is at work not just on this planet, but on that planet also. How well do you think these designs are going to cross the reality gap? I see a lot of you shaking your heads vigorously. These things look like they're going to drop into the abyss, right? Why?
They're not really, at least to me, they don't look particularly statically stable.
Ah, okay. So remember statically stable. Remember our discussion about legged locomotion? To be statically stable, you have a polygon of support on the ground, and your center of mass has to stay on top of that polygon of support at every point. It may not look like it, but this simulator was actually made by hand, and they constrained the speed and strength of the motors in such a way that it's always statically stable. It's a little tweak of this simulator, which we don't have too much time to go into. They actually pause the simulation after each time step, and they run the simulator forward in a slightly different way to let the robot settle. So what these robots are really doing is kind of going, stopping. You can't see that in the simulation, but these are all actually always statically stable. Because these were good mechanical engineers, they knew their mechanics and dynamics. They were scared of the reality gap. They knew that if they evolved something that was not statically stable, they probably had no chance in heck of crossing the gap.
It really feels like these are very dependent on having a flat surface with exactly the right friction.
The flat ground with exactly the right friction. What else?
I feel like this requires that the simulation is really dealing well with the connection of things, and kind of they like, especially the crab kind of looks like it has tension in it almost.
Okay, yeah. So there's a lot of things that are not quite accurate in this physics engine. Physics engines were invented in the same year that this experiment was reported in the literature. I know these investigators, they wrote this simulator by hand. This was a brand new thing at the time. People were just figuring out how to do this. So we'll take all this with a grain of salt. You can see they didn't get the connections quite right. You are all physics engines experts at this point, so you can see some of these things, inaccuracies in the simulator. What's wrong with the joints? What's happening at the joints? Or what's most visible at the joints that is not going to be real in reality?
Clipping,
What do you mean by clipping?
the different bars are kind of interpenetrating.
They're interpenetrating, right? Collision detection and resolution, really hard to do right. In 2024, people are still working on this problem and reporting papers in the literature about how to do this better. It's tricky, hard to do, yeah? So there's a lot of things here that should be causing you to catch your breath and be nervous as we approach the gap. But that's what the GOLEM project is all about, so here we go. Okay, let's look at the arrow first. They observed this one and decided to put in the effort to actually build it. Just as a reminder, everything that you see in white here in the physical robot, this is thermoplastic. So the 3D printer has printed all of the white chassis of the robot, and you can see they've snapped in some motors and electronics, and this thing is dragging a bunch of wires that are supplying power and signals to the pistons. How'd they do? The physical robot only travels 1/3 as far as the physical robot, or travels with 1/3 the speed, probably for the reason that Nate mentioned. The friction is different. You can see that they've got this robot moving over a very thick carpeted floor like the one in this room. So the friction is probably slowing the robot down, but also helping. Easier to move over thick carpet than it is over sheer ice. So it's sort of helping. Why? You could argue that this one crosses the gap. It's not perfect, but it's more or less moving in the way that we observed in simulation. Why was this one successful?
It's doing like peristalsis.
It's kind of peristalsis. Yeah, you're right. You might be able to see a bit of a traveling wave across the body. Peristalsis, always a good place to start.
It's robust, like it doesn't need balance at all.
Remember the four desiderata of locomotion, right? One of them is robustness. You got to move without falling down. That's a huge problem for our species. But if you're lying flat on the ground, you don't have to worry about falling over. So it doesn't matter what kind of ground you're on. you won't fall over. And as long as you're pushing obliquely against the ground and ground has high friction, it works, right? So, first thing to take away from the GOLEM project is you can cross the reality gap, and some bodies make it easier to cross the gap than others. If they had evolved a hopping biped robot in their simulator, that's less likely to cross the gap, much more difficult. If it was not statically stable, more difficult. Yeah? So this idea to try and cross the gap a whole bunch of times was sort of brilliant in retrospect, and perhaps maybe this wasn't anticipated beforehand, but actually the choice of body makes a huge difference. Okay. Here's one of our pyramids here, called the pusher for obvious reasons. Okay, but not so great. Not quite in the same direction, slower, less successful. Why?
I think partially because it's less, it has more mass that is in contact with the ground, and it has more friction because of that.
It's got more friction. This one's got quite a bit too, which is also slowing it down. How about the tetrahedron? The clear winner from the GOLEM project. The camera angles, they didn't shoot from the same camera angle, so it looks like the simulated and physical robot are moving in different directions. Very good approximation. Very successful crossing of the gap. Why?
It looks like it's doing an interesting thing where it's like kind of pulling up on the back as it pushes, so it has very little friction with the ground.
Exactly, right? It's pulling itself up, so it's overcoming whatever friction there is and the inaccuracies of friction vis-a-vis what it was in simulation. Pushing a little bit more vertically, but still reliably obliquely, so off it goes.
So it's kind of about whether the strengths of the evolved body align well with the things in the simulation that were accurate versus the things that were not.
Correct. So if it's strong enough to match the things in reality that were correct and it overcomes the things that are not, yes, in this simple case, we are poor, humble humans. Those are the only aspects of this that we can see that affect whether or not this thing crosses the gap. What is harder to see is how close the mass distribution is between the simulated and physical robot, which also affects whether or not it crosses the gap. How much is the set of wires dragging behind the robot, tugging back on the robot when it moves? Maybe a little, maybe a lot, maybe it matters, maybe it doesn't. There's dozens, if not hundreds, of little micro features that are different between simulation and reality that you can't see. All of the observations that you made were great observations, but they're just the tip of the iceberg, right? And they can lead us, and they led many of us at the time to think, oh, reality gap's not so hard, actually. Okay, we're close to a solution. 24 years later, with more complex robots, and we're going to see a more complex robot in a moment, it's not so easy. It's possible, and choosing the right body can help. Okay. All right, so we've spent all our time so far talking about automated design, and we've looked at some of the automatically manufactured robots. This is not a mechanical engineering class, but I think it's fun to just go back in time and have a look at the advances that were being made in terms of 3D printers at the time. So let's spend a little bit of time talking about this second step of the experiment. How did they actually make these robots? Has anybody actually used a 3D printer before? Okay, great. All right, so at the time, this was a brand new technology. This is a greatly sped up version of the 3D printer that was being used at that time. One of the very first 3D printers that existed in an academic lab. And you can see it starting to print one of the cylinders that makes up the robot. Here's a zoomed in version of it building a different robot. You can see here a partial build. Most of you know by now a 3D printer It's called a printer because it was based on the metaphor of an inkjet printer, which splashes ink onto a piece of paper. 3D printer does more or less the same thing. It splashes heated up liquid plastic onto a base plate, which cools fast enough that they can then splash another layer, and up you go. You're depositing 2D layers of thermoplastic. But depending on the geometry, the 3D geometry of the thing you want to build, building it in 2D layers is difficult. So these early 3D printers and a lot of 3D printers today print additional stuff. This is just weak scaffolding to literally hold up the parts that are being built. It took about 8 hours to print each of these robots. They would print it during the day, and then in the evening, they drop this into a liquid solution that would eat away at the plastic slowly. And it would eat away slowly enough that by the next morning, it had eaten away all the scaffolding, but hadn't done a good enough job eating away the actual thing you wanted. So you got this. You got a whole bunch of connected hollow cylinders. That's what 3D printers could do at that time. How do you make a shoulder joint, a passive shoulder joint in the robot? Remember that there's a piston that's pushing and pulling on the bar, but if you have two bars that are attached by a piston and the piston pushes on these two bars, the passive joint has to be able to rotate. So they got very creative in a CAD program and came up with a way of printing all of this stuff to produce basically a shoulder joint. Yeah? Passive. Then they put in the actuators. Here's the little box of electronics that's controlling the actuator, supplying the power. There's a little battery in here. So this little box is placed just out of camera view here. That's the thing that the robot is dragging behind it. Okay. The nice thing that was realized about this at the time is that when this was published in 2000, maybe in the distant future it would be possible to print these things from recyclable plastics. So they put the robot here in a little toaster oven and heated it up. Remember, this is thermoplastic, which has a low melting point. And so they melted away and drained off all this liquid plastic. Most thermoplastic-based 3D printers today can do this. You can actually melt down whatever it is that you printed and send that back in as a raw feedstock to the 3D printer. 3D printers are a little bit scary because it allows us to print lots more stuff cheaply, suggesting there's going to be a lot more trash and plastic waste on this planet. But there is an attempt to make this part of the circular economy, that once you're done with something, you can literally melt it down and reuse the parts. Again, tangential to what we're talking about in this class, but kind of an interesting way to approach robotics in general. If we can do that, if we can melt down and reuse, if we can melt down to recycle, maybe we can reuse it also. Just because the journalists weren't frightened enough by this experiment, they generated this video as well, just for fun. Okay, so that's the GOLEM project, another attempt to cross the reality gap, which is the brute force attempt, right? Just design, manufacture, design, manufacture. 3D printers were being invented at the same time, so I joined the lab that had just finished the GOLEM project at that time. And at that time, they were developing an offshoot, which is, wouldn't it be great if you could make a 3D printer at home the way that most of us have a printer at home? So the Fab at Home project was basically a do-it-yourself project where you could buy a lot of these parts. They're very cheap, and you could assemble them at home with common tools, not that difficult. And if you knew how to use CAD, you could actually make one of these things. And the idea would be maybe 3D printers would become like personal computers in the 80s. What made computers so ubiquitous? It was that in the 80s, everyone started to be able to afford one, had one at home, and started tinkering with it. What could you do with this new thing called a personal computer? The hope was you could do the same thing with 3D printers. That hasn't quite materialized yet. Anybody have a 3D printer at home? Okay, all right. So maybe. Okay, we'll finish with this, this project, the RepRap project, which also started about the same time, and this was conducted in the UK. Let me see if I can speed this up a little bit. The RepRap project, a 3D printer that prints itself. This is, if you ever make it to London and you get to the Science Museum, you can see exactly that machine in the museum. It is arguably the first machine that can print all of its own parts. It still has to rely on those darn humans to do the last little piece, which is to put all the pieces together into a new RepRap machine. Oh, and also buy the parts and so on. So not completely automated. You can see it's a machine made up of a lot of parts with complex geometry and interconnectedness. Just for fun, imagine a hypothetical evolutionary algorithm attached to this. You can evolve the design and function of this RepRap machine to print a copy of itself. What kind of fitness function might you apply to this evolutionary algorithm?
User satisfaction score.
What do you mean by user satisfaction score?
If this is still a product for
Yep.
people who want to do 3D prints,
Okay.
how happy are they with the results?
Awesome, absolutely. Yeah, involve humans in this and get them to put a score from 1 to 10 about how fun it was to build the next version of a RepRap machine.
It's like the score of it depends on how well the child does.
Ah.
The score of the child depends on how well the grandchild does.
So we can assign, you're right, we could keep going. Let's imagine a fitness function that actually is a combination of how well the parent and the child does. What do you mean by does? What would you measure about the parent and child?
I think you would need a benchmark build, like just a template object that they would have to build every generation, and you would measure the speed and the accuracy with which you can build.
Okay, right? So we modify this RepRap machine so that it doesn't just print RepRap components, it makes something else as well. And the speed or the precision or the quality at which it makes this other thing becomes the fitness function. And let's run that hypothetical evolutionary algorithm in our head. Over evolutionary time, we get RepRaps that are able to better build the thing we actually want them to build, faster, cheaper, and so on. That's one possible way to go. What else?
So could we evolve it for the speed at which it can produce another RepRap?
Absolutely. So you can try this yourself. Go to the RepRap website. It'll send you to Amazon to buy all the parts, and you got to assemble them. It takes a while. It's very frustrating. User satisfaction score, I can tell you as a user, is very low. It's very frustrating. Lots of swear words. So maybe we evolve it to facilitate the speed at which you can build another one. This first RepRap, I forget what percentage of parts it's able to print. It can't print all the parts of its child. It's like 70, 90%. Maybe we include that in the fitness function. Evolve self-replicating machines that can print more of their own parts. Evolve RepRap machines that print a version of themselves that's 10% larger than the parent, or 10% smaller than the parent. Lots of ways you could go with this. Okay, that's just for fun. Okay, we've got 10 minutes left. So we looked at the radical envelope of noise hypothesis from the mid-90s. 5 years later, the GOLEM project in 2000. We're now going to talk about the resilient machines project, which was reported in the literature in 2006 by yours truly. This was a project that I was involved with. This was a collaboration between myself and Hod Lipson, one of the workers on the GOLEM project. So I teamed up with Hod. Let's come up with a new way to solve the sim to real problem. I'll show you how the Resilient Machines project solves the sim to real problem in a moment. There was a second goal for this project, not just come up with an algorithm that guarantees that robots transfer from simulation to reality. This was work that was funded by NASA, and so we had to also satisfy NASA. What NASA engineers are particularly terrified of is using millions and possibly billions of taxpayer dollars to develop a very complex and expensive rover. Take 5 or 20 years to send a rover somewhere in the solar system. Rover gets there and things don't work. Something goes wrong. For that very reason, NASA is probably the most conservative engineering firm on the planet. There's redundancy within redundancy within redundancy. Every single project that NASA tackles is super expensive, tons of people hours, and takes, unfolds over years or decades. So they're very, very careful. However, on the flip side, they also know that wherever they're sending their probes, it's a very uncertain environment. So there's lots of things that can go wrong. There's lots of unknowns. So NASA also spends a lot of time working on what they call methods of last resort. If a very expensive rover is sitting somewhere in the solar system on an extraplanetary body, and the mission is about to fail, you're about to lose the whole thing, then and only then will NASA consider ceding autonomy to the rover, meaning mission control takes their hands off the joystick. Mission control says, I don't know what's going on where you are, but clearly something's really wrong. Rover, you try and figure it out. So they funded us not to solve the sim to real problem, but to develop a method of last resort. What algorithm should you package onto the rover so that someone on mission control can just push a button and it starts that algorithm? The rover or the robot itself starts to try and figure out what's gone wrong, diagnose the problem, and find a way to recover. Okay, so we did that. Here it goes. So here's the robot, which has taught itself to walk. And as you can imagine, we did this in simulation first and then transferred it to reality. So the mission here is just get from the left side of the table to the right side of the table. This is phase 1 of the experiment. In the GOLEM project, this was everything. In your assignments, it's everything. That's all that matters. But what happens if, after it's evolved the ability to walk, something goes wrong? So you'll notice now that we sent a grad student in with a screwdriver, and he has mechanically separated the right lower leg of the robot, and the motor that used to sit at the knee of the robot is still connected to the robot. The robot is still sending commands to the motors, but it's not walking anymore. Something has gone wrong. You can clearly see what's gone wrong, and you might even be able to dream up a way for this robot to walk with 3.5 legs, rather than the original 4 legs that it has. The trick here is that the robot can't see what's gone wrong, and neither can mission control. So I just want you to assume that you can't see what's actually gone wrong. The robot is sensing that something has changed. The kinds of sensory information that it was getting from here is different. Something has happened. So the robot has 2 problems it's got to solve. It's got to diagnose what's gone wrong, and it's got to come up with a compensating controller. It's got to come up with a new way to move because its mission is still the same. Get from the left side of the table to the right side of the table. So in this 10,000-foot view of this experiment, which is made up of these 3 parts, between the second and third phase of this experiment, the robot has successfully figured out what's gone wrong, and it's come up with a way to recover. I haven't told you how it does that yet. It's not going to win the Dancing with the Stars competition. Not the most graceful machine you've ever seen, but it does recover the ability to move from the left side of the table to the right side of the table. It's moving slower. It's not moving as straight as it does before, but from NASA's perspective, this is way better than having to hold a press conference the next morning and tell the US taxpayer, sorry, game over, we got to start again. Perhaps this machine can still extract some of the science or whatever it is that the rover is meant to do. So far, so good? Okay. All right, we got 5 minutes left, so let's dive into each of these 3 phases of the experiment to see exactly how the robot diagnoses unexpected problems, and recovers from them. Okay. Before we dive into the details, let's just sort of step back for a moment. We're going to see how this experiment contrasts to all the other evolutionary robotics experiments we've seen so far. One of the things that tends to underlie everything we've seen so far is evolve a controller for a robot, or evolve the robot itself, like we just saw in the GOLEM project. Evolve the controller and or robot to automatically discover near optimal behavior. We never know whether the evolutionary process has found optimal behavior. We just hope that it's getting better and better. How? How do we go about doing this? At the time, there were 3 existing ways to do this. Evolve controllers directly on the physical robot. Obviously, the first experiments that we saw in this field, that's what they did, because there was no other way to do it at the time. There was just the physical robot. With the advent of the problem with this, of course, is it takes a long time to do this. We got to evaluate hundreds or thousands of controllers on the physical robot. First of all, NASA hates this. Imagine you have a damaged rover that is sitting on the slope of a crater on some planet or moon, and the robot just starts to randomly try things. It's the last thing NASA wants. Most of the things a machine might try are going to make things worse, not better. Yeah? So this is unsatisfying for us as roboticists. It's labor intensive and also very dangerous for a machine in the wild to do. So the most common solution we've seen in this class is create a simulation of the robot and do all of the evolution in the simulator. Then cross your fingers, transfer the controller to reality. But of course, there's a problem with that approach, which is the gap, right? Okay. There's another problem with this, which we haven't really mentioned, which is you need to make the simulator itself. For the grad students that are on D5, you've spent D1 through D4 making a physics engine from scratch. For the 10 assignments, I gave you most of the physics engine, but still it took a lot of effort to actually make the simulator before you actually started to evolve the robot. So there's actually 2 big problems with evolve in simulation and then transfer to reality. Third approach we haven't talked about in this class, but used to be popular, is create a controller by hand. Use your genius as a robotics engineer to figure out how sensation should be transformed into action to produce whatever behavior you want. And really hard to do, but make something that's kind of okay, and then allow evolution to tune up that hand-created controller on the physical robot. Obviously, there's a problem with this approach as well. What is it?
It requires an immense amount of intuition from the creator.
Absolutely. Super, super hard to do.
Isn't that what reinforcement learning pretty much tries to do?
Yes, and reinforcement learning is very successful, but requires the physical robot. Reinforcement learning has not yet figured out how to learn the body plan itself. So there's an implicit assumption in here as well, is that ultimately all these methods have to decide on the body and brain as well. As we just saw in the GOLEM project, the body matters a lot. But you're right. If you think you have the right body plan for the job, then you probably don't need evolutionary robotics and you can go use reinforcement learning. But if you don't quite know what the body should be, and actually that's true for NASA, they tend to send wheeled rovers, but there's now an ornithopter up there as well. NASA's in the process of trying lots of different body plans for robot probes as well. It's not clear what the optimal body plan is for exploring a particular planetary body. Okay. So the Resilient Machines Project, it's got a lot of different names and there's a lot of different goals. So we just saw one of the goals of the Resilient Machines Project, which is to enable a robot to recover from unexpected situations. The other thing that I designed the experiment, the Resilient Machines Project, to do was to try and overcome these problems. We used to call the Resilient Machines Project the estimation exploration algorithm. It's a mouthful and it's kind of boring and it doesn't really capture what it does, so you can sort of skip over this. What you're going to see in the Resilient Machines Project is we're going to, this algorithm is going to evolve controllers in simulation and transfer them to the physical robot, like we've seen now a couple times. But the algorithm is also going to evolve the simulator itself. We are not going to create a simulator from scratch. We're going to evolve a simulator. What do you think the fitness is of a population of physics engines? If you're going to evolve a good physics engine, what do you want that physics engine to have?
Given specific conditions in the real world, how well does the simulator's next time step match the actual experience of the next time step?
Absolutely. So you're going to see an evolutionary algorithm inside the Resilient Machine Project, which is not evolving robots. It's not evolving controllers for robots. It's evolving simulators to be accurate. How do we know if a simulator is accurate? We need information from the real world. So what you're going to see several new things in the Resilient Machines Project. The thing that we'll see at the beginning of next time is not sim to real, but real to sim. The physical robot is going to collect sensor motor information and send it back to the evolutionary algorithm. And that evolutionary algorithm is going to use that as raw material to evolve an accurate simulator. We'll pause there for today. You have a quiz due tonight. You're working on either A10 or D5. We'll talk about the final project when we meet again on Tuesday. Until then.